Then let me present the next, introduce the next speaker. The next speaker is Telemachos Panagiotakos from Denko PC, Greece. His speech is about the assessment and retrofit of bridges. He's a CEO and head of the Bridge Design and Special Projects Department of Denko Structural Engineering, PC. He is a postdoctoral research associate at the University of Patras, Greece, and the University of Rome La Sapienza in Italy. He was also lecturer at the Department of Architectural Engineering of the University of Patras. He has extensive experience in the study of complex technical projects, both in Greece and abroad, as well in research on earthquake engineering. He has been involved in the structural design of bridges, building complexes, as well as in the assessment and structural upgrading of existing structures. He has been involved in the drafting of the Eurocode 8 Part 1 and Part 3, as well as of the Greek Code of Structural Interventions. He is national representative of the Eurocode 8 Committee, Earthquake-Resistant Design of Structures, of the European Committee for Standardization, and member of the horizontal group bridges within the CENTC 250. He is also member of several scientific organizations. I welcome Telemachos Panagiotakos, and I yield the floor to you. Thank you.
Thank you very much for this nice introduction, and I would like to thank you also for giving me this opportunity to present the assessment and retrofit of bridges as it appears in the next generation of Eurocode 8 Part 3. This new clause, the clause 12, gives specific rules for bridges, consists of, let's say, 6 sections. The first section covers the scope, the second, the performance requirements, the third, the compliance criteria, the fourth gives information for structural assessment, the next section covers the assessment procedures, and the last section covers the design of structural intervention. How everything starts regarding the bridges and the apologize for this. How everything starts. We have the mandate M515, where it's requested the extension of the scope of Eurocode 8 Part 3 to cover the assessment and retrofitting of bridges. Through this mandate, it requests that the provisions shall be mostly applicable to concrete and steel composite bridges. So we don't cover essentially masonry or let's say timber bridges. But they ask to also cover the retrofitting of foundation and bearings, and also to introduce the base isolation and the addition of dissipative devices as part of the retrofitting solution for bridges. Therefore, we have a new clause, the clause 12, which is something that does not appear in the current version of Part 3 of Eurocode 8, and we change also the title of the Eurocode 8 to add the bridges, and now the Part 3 covers both buildings and bridges. So the clause 12 contains provisions additional to those appears on the other relevant parts, and I mean that we don't find in this clause details regarding, let's say, the materials, because materials already covered in the previous part, and distinguished colleagues presented for steel, for concrete, very detailed about how we deal with the assessment and upgrading of structure of concrete or steel composite structure. So here we have only additional provision dedicated to bridges. The clause 12 primarily covers the seismic assessment and retrofit of existing bridges where, and this is very important, in the horizontal seismic action are mainly resisted by the piers and or abutments. What does it mean? it essentially does not cover arc bridges. Also, suspension bridges, timber, masonry, as already said, movable, floating bridges are beyond the scope of this clause. This is defined in the scope of clause 12 of part 3 of Eurocode. So we have a chain of sections in order to follow the provision for the specific rules described or defined in the clause 12 and related to bridges. In the first section, we cover the performance requirements. Essentially, we set here the targets, which is the performance requirement. And we have two targets, the limit state and the seismic action. The limit states, as already mentioned before, in the Eurocode, the part 3, we have now 4 limit states: the near collapse, the significant damage, the damage limitation, and full operational. We can select one of them. We have already here that the near collapse is preferable, but the relevant authority can, or the owner can choose another one. The issues related to the seismic actions essentially covered by the importance of the bridge, because the influence of the importance of the bridge expressed either in terms of the return period or a performance factors. Therefore, essentially we set in this way the seismic action. The second section covers the compliance criteria, and here we have two critical aspects. The first one, and two critical, I say, distinction that we have. The first, the distinction between ductile and brittle mechanism. We know this, we have already heard about this distinction in the members, but what is very critical in bridges is that this distinction, as already applies on buildings, this distinction between ductile and brittle mechanisms apply to the individual structural members, not to the whole structure. The second distinction, which is more critical and it appears here in bridges, is between primary and secondary members. What is the definition of this? It's very tricky. Except those listed as secondary seismic member, all structural members of the bridge should be designated as primary members. And where we have the definition of this definition comes in the part 2 of Eurocode, which is related to the design of new bridges. And there you can find a detail about the definition of the primary and secondary members. We have also a subcategory of the secondary members, and this subcategory is what we have as sacrificial members. Sacrificial members are subcategory of secondary seismic members. Both secondary seismic members and sacrificial members may be neglected in the modeling of the bridge, since they do not form part of the lateral resisting system during the earthquake. Secondary members, however, need to be capable of sustaining gravity loads and the horizontal displacement induced by seismic action, implying that their collapse is not permitted, because the secondary members, we think that it's there and they still there after the earthquake in order to carry out the, in order to support a member. For this reason, it's expected that secondary members are going to be included in the model, neglecting their stiffness, because this is why we said that it's a secondary, it is not participating in the horizontal resistance of the bridges with respect to horizontal loading. On the other hand, the sacrificial member, because we have this distinction here, we can designate a member as a sacrificial member. The sacrificial members are allowed to fail under the specified conditions if they do not support other members. So it can fail, and you don't need it anymore. They are usually included in the structural model prior to their failure, not of course after their failure. Examples of sacrificial members and designation of sacrificial members are very common in bridges. Here are the backwards, as already the Professor Kappos said before, as well as CRKs. I remind you that both secondary and primary and secondary seismic members, the definition appears in part 2 of Eurocode and not in part 3. The third section of this chain for the assessment and retrofitting of bridges are covered the information for structural assessment. The information for structural assessment, for obtaining the information for structural assessment, the extent of an investigation scheme that we have to follow or to decide, considering the target knowledge level for each bridge component. It should be noted that there may be different knowledge level, as already Professor Franklin said, for different structural components. The finally obtained knowledge level should be determined based on the amount and reliability of information collected regarding the corresponding data on geometry, materials, and details. The specific provision for this are covered in other section of part 3. Now, regarding the investigation scheme, here in bridges we propose a 3-step in order to obtain the highest feasible knowledge level, which is the target of investigation scheme. These steps are the collection. In the first step, we have the collection of information and the first inspection, visual inspection of the bridge. In the second step, we have the simulated design. And in the third step, we have the detailed survey and more investigations. So, going to the first step of this procedures of investigation. The first step consists of gathering of available information concerning the existing bridge and performing the first visual inspection. So cover these two aspects. Gathering of information should include collection of all available information related to the bridge. What I mean, all available information we can find, if available, as-built drawings, design construction drawings, calculation notes, specification, site report, damage report, soil boring and test logs, geotechnical report, hydrogeological report, maintenance record. What we have, it should be gathering in these steps. And during the first visual inspection, what we are doing, we have a geometrical and topographical survey in order to establish the geometry of the bridge. In the absence of verified drawings, new general arrangement drawings should be developed after the survey. All structural defects, and this is very important, also should be recognized during this first inspection. In the second step, we have the simulated design, which is consists of the second step essentially is a simulated design using the results of the previous step with a geometrical survey and the first visual inspection in order to verify uncertainties of the geometrical and topographical survey and design assumptions. What are the design assumptions in bridges? For instance, the geometry of tendons, the pre and post tensioning of post-tensioning forces for the tendons, the reinforcement and the critical area of reinforcement, arrangement of the reinforcement, hidden or unavailable details. This can be done through a simulated design, which is a kind of back analysis. We're using the standards and the a specification of the original design, and we repeat the original design essentially. This is a kind of simulated design. This is a part of what is already in Annex A presented as preliminary analysis, but a little bit different. Of course, if reliable as-built drawings are unveiled, this step may omit. The third step should consist in completing from one hand the geometrical and structural survey, and from the other hand investigations. The detailed geometrical and structural survey may be necessary for assessment of hidden foundation details. I'm focused now in foundation, which is very critical in some cases. And this can be done through shafts or using georadar, ground penetrating radar, etc. And locating tendons and reinforcement through electromagnetic scans and cuts, or try to find out the tendon forces through cross-bow methods, etc. The investigation should be performed where insufficient information is available to determine if the existing structure can resist seismic action, or preliminary evaluation indicates that retrofitting is required. And the investigation essentially cover properties of material and how we can find the properties of the material. We can estimate the concrete qualities and properties through various methods that exist, destructive or even non-destructive, like concrete coring, which is destructive, ultrasonic pulse velocity measurement, which are not destructive, pull-out test is destructive, a Smith-Hammer test not destructive, pull-off test is destructive, etc. I have to note here that all these methods covered by appropriate standards, ENS or ISO, so it's written in the part 2, in part 3, the standard that you can follow to achieve the, to find out the test and how to calculate through the test the properties of materials. Another critical investigation that we need is the estimation of type, grades, properties, and condition, of course, of structural steel, reinforcing steel, and tendons. We have here also similar methods. During the investigation, we have also the need to estimate the condition of bearings and connection. And finally, I saw also a question, and this is what we request here. It's an investigation for the estimation of the effects of age and durability of the structure, which is critical. So for concrete structure, we need the carbonation depth, the chloride content at different depths of the concrete members, detection of cavities, holes, the lamination of concrete using various methods such as infrared thermography. This is the test requirement in order to achieve the full or almost the full picture for the structure. Finally, there's also other methods that can also be done, like dynamic loading testing, which is give us details regarding the bridge. Therefore, through the investigation scheme that we follow and cover what I said before, the survey and the test, we try to obtain the highest feasible knowledge level for the structure, for the bridge. With the exception of the box-type bridges, 6 types of structural components, and this is very critical, we don't have this on buildings. We have structural component, individual structural component, identified per bridge, and for each structural component, we have a specific knowledge level depending on the information that we gather from the test and survey. So what are these types of structural components? It's the common components that we have in bridge. We are talking the deck, the pier, the foundation, the abutment, the bearings, joint and connection. This is we have to identify this component in bridges, and for each one of them, we have to give information category regarding geometries, construction details, and materials, and the relevant knowledge level, which is we know that there are 3 classes: minimum, average, and high. So the knowledge level for each category information, namely geometry, construction details, and materials, should be representative of, and this is critical, the critical region, not the pier in general, but the critical region of the pier should be assessed, and there we have the to set the knowledge level. For the geometry, and this is another requirement, especially for bridges, we have as a minimum, the average knowledge level should be attained through the investigation scheme. So we have to extend our investigation to attain the average knowledge level for the geometry for all the critical components. For each component and material, the achieved knowledge level on materials, it's described in section 8 for concrete structure and in section 9 for steel and steel composite members. And respectively, for the knowledge level on details, it describes on section 8 again for concrete structures, and in clause 9 for steel and steel composite structures. Now, going in the fourth step in this chain of steps or of action is in order to assess and retrofit the bridges, we have the assessment procedures. One of the, I think, more innovation that we have in this part of Eurocode, it's this distinction between bridges regarding which seismic action is dominant. And what we have here, we distinguish the bridges in single-span frame or box-type bridges, where the main part of the seismic action induced in these bridges comes from the earth pressure and acting on the back faces of their abutment that are in contact with the earth or the embankment. And the seismic design should be based on the formation compatibility approach. Here we are talking for kinematic seismic, for bridges where the kinematic seismic action is dominant. This is one case of bridges. All the other belongs to the inertial seismic bridges where the inertial seismic action is dominant. Essentially, we separate the bridge in 2 big categories. One is the underpasses or the single span or the box type of bridges, and all the others. Now, for all the other, which is the majority of cases, the seismic analysis described in clause 6, we don't have something specially on clause 12. The soil structure interaction, it describes and covers in part 2. We don't have something special here. The model for resisting for both for concrete and steel concrete steel composite structure described on clause 8 and 9. It's permitted to use nonlinear analysis. Of course, if we made nonlinear modeling of the bridge, we have 2 components are expected to yield. If we have a linear analysis, all the other components in nonlinear analysis should be linear elastic. A few provisions for the displacement based design are also included in clause 12. material properties, deformation capacity, already presented in previous chapter. We don't have here special provisions. Again, the shear verification also here we have to mention that I have to mention that especially for shear verification, we have to refer to part D of Eurocode for the bridges. And finally, the axial force of the piers. This is something that we now clear also to the part 2 for new bridges, may be taking as constant. Now, what happened in the other small category, but other category? I talk about the one span or box type or frames underpasses. I'm talking for kinematic, where I'm talking for bridges where the kinematic seismic action is dominant. This is a special case. A realistic estimation of the seismic action effect for those bridges requires consideration of all soil structural interaction and of the dependence of earth pressure on the back faces of the abutments, on the compatibility or deformation between soil and bridges. The analysis method for this kind of bridges, either force-based or displacement-based, is presented on part 2 of Eurocode 8, so you can follow what is written there. Why we have separated these bridges? Because essentially we have to take into consideration the resistance of soil for these bridges, and this is very critical, and this is why we have a separate category for these bridges. Otherwise, these bridges, ignoring the resistance from soil, can be very demanding in the seismic situation, and this is not true in reality. And going to the final step in this procedure for the assessment of the bridges, we have the design of structural intervention. And this is for provide in this section, we have additional provision, what is already covered in clause 7 of part 3, which is also general. Now, what is very critical, a good solution we know very well for bridges, for the retrofitting of bridges, for intervention on bridges is the seismic isolation. The design of the seismic isolation, it's covered by part 2 of Eurocode, because in any case, the design for a seismic isolation is a design for a new seismic isolation system that's applied on bridge. So all the requirements covered on part 3. In designing an intervention scheme should be taken into account what? All the deficiency in resistance of primary seismic member, all of the deficiencies should be remedied by suitable intervention, including either retrofitting or reduction the action effect, which is it's not seldom in bridges. The intervention index should be remedy deficiency related to permanent action that may also be necessary to avoid kinematic problems, and this is something that we have to take into consideration, kinematic problems like impact or loss of support. And the strategy of seismic retrofitting, which does not require a retrofitting of foundation, should be preferred. This is a very critical, I think, for the people that related to the design or to the intervention on bridges. It's something that we know very well. So now the chapter close with the intervention of the structural components. The intervention on piers may include what? Complete of partial replacement, addition of supplemental pier, shear and flexural retrofitting, improvement of pier ductility through confinement, reduction of action effect on pier through seismic isolation. If we isolated on the top of the pier, we have for sure a reduction of the action effect. Now, for reinforced piers, the typical retrofitting technique through jacketing, and again, there's not a provision that the preferable techniques, retrofitting techniques, are those that increase the ductility and or strength, and do not substantially affect their stiffness. We don't want to increase the stiffness, since if we increase the stiffness, we increase also the seismic action. Now, the intervention on foundation, enlargement of foundation, shear and or flexural strengthening of foundation, addition of piles or micro piles, improvement of critical soil volumes like makes jet grouting, injection of soils, etc., and of course complete or partially replacement. Don't forget, when we have the intervention on foundation, we have to also include the soil itself, as this is we have to avoid flexural shear sliding failure on soil. Also, to take into consideration potential effects from liquefaction, for lateral spreading, for cyclic softening, and landslides. But all these issues covered on Part 5 of Eurocode. Regarding the abutments, there's also here various intervention proposals on the abutments. Shear and flexural strengthening, longitudinal support at the top of the abutment, adding soil or rock anchors, replacing part of the earth fill or the embankment with special forms, lightweight forms like expanded polystyrene, or using reinforced soil, and complete, of course, and or partial replacement. For the body of the abutment, the retrofitting techniques are the same as we have in piers and foundation. Again, there's a recommendation here that we have abutments to be retrofitted. We prefer to retrofit it by reducing the earth pressure. This is something that is very good for existing structure. Going to bearings, what we have to do? Replacement by new bearing, or replacement by seismic isolation bearings, or add addition energy dissipation device. What is critical here is the intervention to bearings may be required to assure that the force of the deck are effectively transmitted to the piers. We have maybe to also to intervene the deck and also to piers. And finally, regarding the deck, what we can do for intervention, first of all, we can try to reduct the dead loads if we have more additional load for some direction of the deck and we don't need it yet anymore. Provide horizontal longitudinal continuity of the deck in order to avoid impact and unseating of the deck. We can also retrofit or remind the deficiency of deck. Retrofitting also the deck pier joint if we are connection there. Increasing, of course, the overlap length if it's not adequate. Use restrainers also in order to avoid the drop of the deck. And again, a solution, the last solution is a complete or partial replacement of the deck. Again, here it is given special note to avoid the unseating and to check the unseating of the deck, because it's critical for existing structure. And I'm closing with this slide just to give you an idea that all what presented here as intervention techniques is applicable techniques, are applicable techniques, are not something that is only in papers, is already applied in many bridges around in Europe and not only. And I give you just a few, 2 bridges here. It's already presented in the European Earthquake Engineering Conference in Thessaloniki. One is we use seismic isolation with a friction pendulum system to upgrade an existing bridge, 3-span bridge in northern Peloponnese. And we also applied the EPS on the backfill of the abutments in order to update the abutment. And the second is a very conic bridge also in the same area, where we have to intervene not only to piers, where we use FRPs, etc., but also to the foundation through additional piles, etc. Thank you for your attention.
Thank you very much, Telemachos, Panagiotakos, for your very clear presentation and for the topic that is really a hot topic in many seismic-prone countries in Europe, where the bridges have overpassed their service lives, by the way. I'm sorry there is no time because we are a little bit behind the schedule. But anyway, don't feel disappointed, because if you want to make questions, you can find the contacts of all the speakers in our website about the EC8 webinars. So thank you again, Telemachos. We move now to the last speaker of today's webinar,